Okay. Here we go. All right. So the last couple of classes we've been talking about how we come up with designing databases is not trivial, right? And the easiest way to do it is to use a graphical representation of the data through the use of class diagrams, right? There are other class diagrams we're going to take a look at, like sequence diagrams, state machines, and things like that. But for representing the data and its relationships, the class diagram is a better solution. And when we're looking at designing these class diagrams, we're always considering redundancy, right? We want to avoid redundancy at all costs, because we know that redundancy breeds inconsistency, right? That if and we look at we consider all the various paths, right? That represent the various queries that we might have, right? That if I have to query for some data, I'm going to have to join this table with that other table, right? And we're always asking ourselves, well, can I join these other two tables and answer the same question, right? And the same query? And if the answer is yes, then you have redundancy in your class diagram, right? In your data model. And we look to remove that redundancy, right? Because just like you can update it in one particular way or another, you can also, just like you can query it one way or another, you can also update it one way or another, right? And that's where the problem might be, that one developer might choose to update it one way, right? But another developer might choose to update it another way, because it's just as efficient, right? It might be updating these two tables or those three tables, right? You get the same effect, right? But it might end up that they're not consistent the way they're doing it, right? So that if you query it one particular way, you get one answer. If you query some other way, you get a different answer, right? Those are the inconsistencies that you want to avoid. Well, not only is there inconsistency across, when you're joining or when you're considering navigations from one table to another table, or not only is there inconsistency across tables, but there might be also inconsistency within the same table, right? And that's where I want to start looking at today. And before we look at redundancy within the same table, we need to consider what we call functional dependency, right? Is there data, right? Are there fields that are related to one another, that are one dependent on another, right? Meaning, if you know one of the fields, might you know the other field, right? For instance, if you know that a car is a Corolla, would you not also know? Doesn't that imply that it is a Toyota? It does, right? So if you have two fields next to each other on the same table, yes, where one is the car model, right, and the other one is a car maker, two fields next to each other, and you need to update both of them, right? If you update one that says, this is a Toyota, this is a Corolla, well, the other one would have to always be a Toyota, right? It would make no sense that one is a Corolla, but the car maker is a Ford. Okay, that makes no sense, right? So not only do you have now what we have discovered is redundancy, right? Where you're already telling me that it's a Corolla, it is implied that it is a Toyota, right? If they're in the same, if these are two fields of the same table, of the same record, then you could run into inconsistency, because one implies the other, right? There is a dependency between the two, and these dependencies between the two, you have to be very, very careful, right? That you either use primary key, foreign key to enforce the relationship, right? To make sure that if it's one, then it has to be the other, right? You cannot have inconsistency, right? Or you would have to split it into separate tables, right? So we'll look at that, right? The fact of splitting into various tables, we call that normalization, right? And normalization is our attempt, right? Of removing these inconsistencies, or removing these dependencies of fields one with the other, so that they're appropriately represented in its own particular class or its own particular table. But the way we first have to identify these dependencies before deciding that these might have to split into different tables. That makes sense? So that's why we're going to talk about functional dependencies first, right? And then right after that, we're going to jump into normalization, right? Normalization depends on us identifying the functional dependencies, deciding whether it's okay or not, right? And then if it's not okay, then the step is to normalize. Make sense? All right. So functional dependencies first. Right. So we're looking for data or redundancy not only across tables but also within tables, right? Fields within the same table, right? And so a redundant relationship, you have redundant fields, right? When you have classes or when you have tables, we remove those relationships, right? The connections, the foreign key, primary key, right? The path, we remove it. But not only is there redundancy across tables, but it's within a table itself, right? And these dependencies are a little harder to identify. Okay? These are dependencies that are within the same table and that they're a little more subtle, right, to identify. Okay, so for instance, you might know that a particular student might be enrolled in a particular course, and that and by logic, you might deduce that it's this student enrolled in this particular semester. They have to be in these particular courses, right? So it might be redundant for me to tell you both things, right? That it's in this particular semester, it's this particular student, and it's enrolled in this particular course, right? It might be redundant. So for instance, if I know a particular student, I might already know that they're in a particular semester, right? So meaning that if you tell me the student's ID, I might already know that they're in a particular semester. So we say that there's a dependency between knowing the student and knowing their semester, right? Or you might say, if you know the professor, you might know the courses that the professor teaches, right? It might be redundant for me to tell you both things, right? Later on, we'll see an example. If I know it's Einstein, then I know he's teaching physics, right? It would be redundant for me to capture those two things in two different fields, right? It might be a better solution to capture the professor and then courses and create a relationship between the two, right? Now there's no redundancy. They are not two fields in the same table, but they're across tables, right? So let's look at examples of this, right? This is the things that we want to identify. If you give me a field, can I deduce the other field, right? Is one a function of the other, right? If I know one, will I know the other, right? By logic. And the only way you can answer this question is if you know the domain, right? If you understand the business logic, right? If you know, like for instance, the example I gave earlier, right? If you know the professor, you'll know what particular courses they teach, right? Is there a dependency? Is there a functional dependency across these? For instance, here you have a student and a particular lecture. If you know, for instance, the lecture, perhaps you might already know that a particular TA is the TA for that particular lecture, right? Or if you know that the combination of student and lecture, you know the TA. Or if you know the student and lecture, you also know the TA and you know the semester, right? So there's a functional dependency between knowing the left-hand side and determining what the right-hand side. So here we have the variable, right? And you have the determinant, right? This is determined. The right-hand side is entirely determined by knowing the left-hand side. So we say formally, we say that on the left-hand side we have the determinant set, right? And then the right-hand side is the dependent set, right? So we have y and x, right? Y depends on x, right? If you know one, you know the other, right? If you know X, then you know Y, right? So the variable is on the left-hand side, and the dependency that depends on the variable is on the right-hand side, right? If you know one, you know the other. You can read it both ways. You can say that X functionally determines Y, or you can say that Y functionally depends on X. Right? You can read it either way. Right? It's the same thing. If we know X, then we certainly know Y, right? Okay. And we say that there's a relationship that binds X to Y, right? Given X, you also know Y. And we need to identify these. We need to identify for each field, once you come up with a class diagram and you're all set and you've removed all redundancies across tables, you still have work to do, right? You still have to look at the fields in a table and find if there are any dependencies across the fields, right? Between fields. Make sense? Right? Sometimes it's okay, sometimes it's not okay, right? We'll see when it is okay and when it's not okay. Right? It all depends on whether one or both are primary keys, right? Or a combination of both is a primary key, right? But if there are no constraints, between the fields, right, then you are certainly at risk of redundancy and inconsistency, right? But if one of them or both are primary keys, then you can enforce certain uniqueness, okay, or that you can enforce that the combination of the two is unique, right? Then it's okay, right? You won't have, for instance, if you have that the combination of car maker and car model, right? The combination Toyota and Corolla, right? The combination has to be unique, right? You won't, for instance, allow me to insert again that the Toyota is again a Corolla, right? Or that one of them is a foreign key to a well-known car maker, right? Then you might say, well, it can only be Toyota, right? Then it's okay. So let's see when it's okay and when it's not okay to have these dependencies. So for instance, we might have here a function dependent for is a constraint between two sets of attributes. Right. So in the examples that we've seen so far, we don't have any functional dependency. Right. Our class diagram that we've been working on for the toy university database, right, has no functional dependencies. But we're going to come up with some rules that are going to introduce dependencies. Okay, so we're gonna on purpose we're gonna paint ourselves on a corner and see what happens. Right. So for instance, imagine that in our original discussion, in our original paragraph describing the university database, right, we have the additional sentence. It says, a professor can only teach one course. Right? That's a new rule. That's a new rule. So we can enforce this by having this, right? For instance, you have a section, right? In that section, if you remember, it said who taught that section, right? The year offered. What else was there? I think that's it, right? And there's a foreign key that goes from that section to the course, right? And if you remember, I believe there was a star here, and there was an enrollment table in between, right? But over here, we're saying that you can only teach one single course, right? So that is creating a dependency, right? It's a dependency between the professor and the course ID, right? Because if that professor can only teach one course, right? Then if you know the professor, you certainly know what course they're teaching, because it can only be that course, right? Before we didn't have this dependency, right? Because a professor could teach any course, right? So if you knew the professor, you really didn't know what they were teaching unless you navigated to other tables, right? And you join other tables, right? But now, because of this new rule, right, our database, our perfect database that we had originally, has a functional dependency, right? If we know one, we know the other. And now, before it wasn't a problem, but is there a problem? Is it a problem now? Well, yes. our database would allow certain things like this. Our original database, right, where any professor could teach any course, right? You could certainly have Einstein teaching physics. Also, it would be okay for Einstein to teaching dance, right? There was no problem. That was not an issue in our original database, okay? And because it wasn't an issue, we didn't have any constraints between courses and professors, right? It could be any combination. We didn't have any. It's saying that the combination has to be unique or anything, right? We didn't have any checks. But now, because of this new rule, and there is a logical functional dependency, this is unacceptable, right? That Einstein teaches dance, right? This is unacceptable, right? But notice that our database, in our database design, there's no way for us to stop you from introducing this data. There's no way that we can stop it, right? Because we introduced this new rule, we have identified functional dependency, meaning, there's a functional dependency. None of them are primary keys, right? Neither one is a primary key. There's no way for us to enforce any constraints, or well, we're not enforcing any constraint, right? So we are allowed to introduce bad data, right? Right? It's not going to stop us, right? Unlike with foreign keys and primary keys, with primary keys and foreign keys, where you create constraints and the database stops you, right? It doesn't allow you to insert or delete things from the database, enforcing the relational integrity, right? Right, enforcing these rules. Over here, there's nothing from stopping us from introducing bad data. Make sense? Now, this data is bad because we introduced the rule, right? If we would have known that rule from the beginning, this is not the design we would have chosen. Okay? All right? But imagine we did paint ourselves into a corner and we kind of forget about that rule, and this is the design we came up with, right? If we came up with this and we start looking at the rules, and somebody is gonna identify and says, wait a minute, right? That rule creates a functional dependency of these two, and there's no way that you're enforcing this, that you're stopping this from this bad data to get inserted into here. Does this make sense? Right? Whenever you find functional dependencies like this, it is a clue that perhaps you need to normalize, right? Perhaps professors do need their own table. Okay? Right. The functional dependency is if you know the professor, you know the course ID, right? So in the anatomy is that you have the left-hand side determines the right-hand side. The left-hand side, right, determines the right-hand side over here. All sections in a all right, here's another one. Here's another rule. It says all sections in a year must be taught by the same professor. Right? So you're in a section, so for a particular section, right? If you know the year, then it can only be taught by that professor within the same year. That means that if you know a particular course and you know for a particular year, then you definitely know the professor, right? So here's one that is a little more complicated, right? The combination of these two, right, determines this, right? For a particular course, for a particular year, right, it can only be taught by that one professor. You see that? So that's a dependency, and we have to first identify the dependencies, all the dependencies, right? And these dependencies are, looking at the schema that you have so far, right? Looking at the original description of the requirements, right? And identifying, says, oh, look, this is dependency here, 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 listing them, and some of them will be okay, some of them will not. Okay? Some of them are says, oh, this one's fine, there's no redundancy, there's no inconsistency risk here, whereas this one, there are inconsistency risks. The ones that are risky, right, that give you inconsistency risk, those need to be normalized. Okay, all right. So let's keep going. Right. So in general, we have that the left-hand side, you can have any number of fields, x1, x2, x3, right? Determines what the the right-hand side is. Notice that this would be a really good clue, right? That the left-hand side, right? If you want to determine that the combination might be unique, right? This is a clue when you identify these functional dependencies. The left-hand side, you see those X's over there? That's actually a clue that these guys, a combination of these three guys, right, might be a good key, right? A good primary key, a combination of these, right? So that you can start enforcing uniqueness, right? So that you won't have the redundancy of for the same X, Y, Z, you would have one value of Y, but for the same X, Y, Z, you might have a different value of Y. That makes no sense. How could you possibly have, for these two things depend on each other, right? It might make no sense, right? That if there's a functional dependency, that if you have the same function and you give it different for the same values, you would expect that it would answer the same answer, right? If the function is addition and you give it 3 plus 5, you would always expect 8. It would make no sense that for the same 3 plus 5, it would give you some other answer, right? There's no statefulness here, right? It's functional, right? For the same input, you would expect the same output, yes, right? Same thing here. If we're given the same left-hand side, you would expect that the right-hand side will always be the same one. So notice that it would be a clue that the left-hand side, right? Those fields on the left-hand side, it's a clue that this would be a good choice for a primary key, right? Even if it's not currently a primary key, right? It's a clue that it might be a good primary key to consider. There's a couple more dependencies, right? Right. So the other way around, right? If you know the year and the course, you know the professor, right? But the other way around is true, right? If you know the professor and the year, well, you know the course, right? Obviously, right? It's mutative. If you know the course and the year offered, then you know the section, right? So these are all dependencies. So presumably, one typical question in a midterm might be, here's the tables, right? And I give you a paragraph and I describe the domain to you, right? And I ask you, well, identify for me the functional dependencies, right? From the description, right? From the rules, and given the particular schema, identify the various functional dependencies. That's a typical question. So here's a functional dependency. Given a professor, given the year, you know the course, right? And so, for instance, if you know the professor and the course ID, then that Einstein was teaching physics in 1950, and Bohr was also in 1951 was also teaching physics. If you know the professor and the year, you know what they're teaching because of the dependency. But the other rule says if you know the course ID and you know the year offered, there can only be one section, right? So notice that these rules, the data that was already there, did not break the rule, right? But if you consider this rule together with the other rule, right, where course ID, year offered, the section, there can only be one section. Then that means that for 1950 and the particular course physics, there can only be one section, section 120, right? Everything else, like section 121, 122, would be violating this particular functional dependency, right? That data would be bad, right? Would not be allowed. So that means that if we have this rule, we need to see how are we going to enforce this rule. How are we going to enforce this rule that we would not allow you to enter this data in there? You see that, right? And the way we're going to enforce it is by normalizing. Okay, which is the next topic. But first, we have to identify the functional dependencies. Okay, right. So as I was suggesting earlier, right? The left-hand side, right, which is x1, x2, x3, right? Those are candidates, right, for keys, right? Because you're saying, well, for a given combination of the left-hand side fields, x1, x2, x3, right, or k, right, k being a subset of all the keys, right? Right. If you say that there's a functional dependency, you might want to say that for a given combination of x1, x2, x3, you would expect to have the same y on the right-hand side, right? So these left-hand side give you a clue that perhaps these could be a good choice for keys. So yeah, so functional dependencies allow you to identify what you might want to choose as keys for your table. Okay, so yeah, so this is the general case is that if you have a functional dependency where you have on the left-hand side k1, k2 all the way through kn, and you have the values on the right-hand side that depend on x1 through xm, then it's a good choice to choose x1 through xm as a key of your table. Sorry. Stop this. Sorry. Right. So if the case is that the left-hand side, right, for instance, you have professor and year offered, right? Wait a minute. Right. If you have the left-hand side is a key, right? If you already have at the left-hand side is for instance the combination of professor and year offered, right? If that's a key, right? You're saying that your dependency depends on this key, and because it's a key, you're saying that the combination is unique, meaning that you cannot introduce this combination again, right? Now the originally professor and the year offer was not a key. Yes, originally was not a key, but if it were, right, we would say that this dependency is what we call a full functional dependency, right? That the combination on the left hand side is unique, and because it's unique, it will not allow us to introduce redundancy, right, for the same combination. It won't allow us to have the same combination of professor and year offer, right? Like for instance, when we had earlier year offer and professor, right? We here, right? The reason we could introduce, the reason this allowed us to introduce it, like physics 1950, physics 1950, right? It allowed us to do it because originally the course ID, the combination of course ID and year offer was not a key, right? And neither was the combination of professor and year offer was not a key, right? So you can put any combination of the two, repeat it over and over. But if you choose that the combination of professor and year is a key, right? Right. If you set those to be a compound key, notice that you would solve this issue, right? You would solve this issue because this data would have never been allowed to be inserted in the first place, right? Because the combination of professor and year offer is a key, right? You would not be allowed to insert course 121, section 121 and section 122, right? Now there's a way to enforce, right? This what we call a full dependency. Okay, the problem occurs when the fields on the left-hand side are not keys. If they're not keys, there's no way for me to enforce any of this, right? Right. So, but we know a technique that can fix these dependencies, right? We know a technique that could fix this dependency, but sometimes they cannot be keys, right? We can't force something. We can't just force anything to be a key, right? Sometimes we can, sometimes we can't. Yeah, so full functional dependencies are okay, right? If we find a dependency, yes, and the left-hand side is a key already, there's no problem with that dependency. It's okay. It's already being taken care of by the left-hand side being unique. Right? The combination of all the keys on the left-hand side is unique. Yes? Right? So there is no problem. There's no way for me to insert the same combination more than once. Right? So fully functional dependencies are A-okay. We don't touch them. We leave them. We identified it, and we can check it off as saying, okay. I know there's a dependency. but it's not going to introduce any redundancy, any inconsistency, right? The problem is if the keys on the left-hand side are non-keys, right? They're not keys. Those are problems, okay? That we for instance, we identify that if I know the professor, I know the course. And I cannot, right, if I don't have a rule in my description that these need to be a key, right? Then I can't force these to be keys if the requirements is not there, right? I can't just make up these rules, okay? So we know that if we identify functional dependency, if there's no way for us to enforce a uniqueness, we know that we're going to have the risk of redundancy and therefore the risk of inconsistency, right? It's a given, right? If you cannot enforce uniqueness, right, you know you're going to run into issues of inconsistency, right? So what do? Right? So let's look at how is it that you would run into this issue, right? Let's look at a couple of examples. Where would how would these non-key functional dependencies occur? Why would they occur in the first place? Right? Sometimes it's because right, we chose attributes that should have been classes, right? Right. The first one, meaning that we chose it to be an attribute as opposed to a separate class, meaning we denormalized, right? Right, meaning that it should have been a class. We should be more normalized, right? We removed a relationship that should have not been removed. Okay? Perhaps we identified redundancy, yes, and we said, well, we can either remove this one or we could remove that one. Okay, and we removed the wrong one. Right, and then when we revisit the resulting class diagram, we find these functional dependencies. Oh, you know what? I should have removed the other one, not this one. Okay. So we should consider what if we remove this one, what if we remove that one, or we didn't remove a redundancy that should have been removed. So let's look at an example. Okay, so this is the example I was talking to you earlier about car models and car makers. Right, so let's look how we would run into this issue. Right, if you remember, we were looking at the permit in our database. Right. We were considering students might have a permit might have a license plate and a car model, and let's make it a little more complicated. And that not only do we want to capture the car model, not only do we want to capture that it's a Corolla or a Grand Cherokee or whatever, we want to capture also the car maker. Okay, so we want to capture that it's a Jeep, that it's a Toyota. Okay, all right, we don't really need to, but let's add this requirement, right, and see how it would affect our decision. One way that we can capture it is that we could have a table with all the car makers, right? Jeep, Toyota, Honda, right, Ford, all the car makers. And then for each car model, right, we have a one-to-many saying that, all these cars, right, they have a foreign key telling me what model they are, right? There's nothing wrong with this approach, right? So let's make a bad decision on purpose, right? So following this design, you have something like this. You have a permit, right? Where you have your permit 1, 2, 3, 2, 3, 4, 3, 4, 5. These are all Corollas, okay? And these green ones are all Cherokees, okay? And notice we have all the car models listed here, right? So we have Corolla, 4Runner, RAV4. We have Cherokee, Liberty, Wrangler. All the first three are definitely all Toyotas, right? And the last three are all Jeeps. So there's nothing wrong with our data model here. Okay, it's perfect, right? It's denormalized. But we could have chosen. Remember when we chose that license plate was, we said, oh, you know what? What? I mean, there's not enough information in the license plate to capture. Let me bring that into the permit. Remember that when we did that? And we decided that it doesn't warrant, me capturing an entire record for the license plate. Let me make it into an attribute. Remember that, right? Well, here you could kind of also make the same argument that we're not we're not the registry of motor vehicles. We don't want to have, we don't want to be over normalized, right? Normalization introduces lags, right? Introduces slowness into the system. Let's denormalize, right? We could have chosen that we could flatten this, right? Right now it's very hierarchical, right? Parent, child, parent, child, parent, child. We can flatten it and combine these two into one. Okay, what if we do that? Right, if we do that, right, what we could decide is, says, you know what, I don't want to have all these tables. Let's flatten the relationship, right, and bring permit, car model, and car maker, flatten everything into the permit. It's a sensible decision, right? And notice now we have into the permit table we add car model and car maker. Okay, and we go on with our design, we implement it, and somebody starts looking at this and analyzing this and says, wait a minute, but you have a functional dependency between car model and car maker. Right? If you know the model, you definitely know the maker, right? If you know it's a Corolla, it has to be a Toyota, right? It would make no sense that you have a Corolla and the maker is anything other than a Toyota, right? But notice that that car model and car maker are not keys. You see that? Neither one of them is a key, right? So there's no way for me to enforce the fact that certain things have to be a certain way, right? There's no way for me to enforce anything here. So we have a non-key functional dependency, right? Notice that car model is not a key, right? So this is not depending on a key. So we call it non-key based functional dependency. Right. Well, one of the things that now, right, we're going to have in our database quite a few of Corolla, Toyota, Corolla, Toyota, Corolla, Toyota, Corolla, Toyota, right, all over the place in our table, right? So that's a redundancy, right? But that's not really the problem. The problem is that there's nothing from stopping us from saying something like Corolla GM, General Motors, right? Nothing stopping us from saying Corolla Ford, right? That's the problem, right? That we have inconsistency. We have bad data. Our database is allowing us to introduce bad data, right? And this inconsistency reduces the value of the data that is being stored. You can't trust your data, right? So now when you query, how many Corollas there are, and it comes out to be, whatever, 1,000, right? But then you query in some other way, how many Toyotas, right, as opposed to Corollas, and you add all the Corollas, all the Forerunners, and all the RAV4s, right? And it comes out to be 1,000. If you ask the same question in another way, how many Toyotas there are, it should also come out to be 1,000, right? It would make no sense that all the, right, in one way they add up to be, right, 900, and the other way they add up to be 1,000, right? It makes no sense. So that's what I mean by inconsistency, right? That you can query two different ways, right? And they should be the same answer, but they're not. Which one do you trust? Right? When you start doubting your data, it loses its business value, right? So yeah, so inconsistency. We can fix it, right? One way to fix it is just ignore it. It says it might not be important enough. Okay, for our business, it might not be an issue, right? It's once in a while we have an inconsistency, but it doesn't affect our day-to-day operations, right? It's not a fatal issue that we from time to time might have the wrong make for the right car. Okay, so it might not be an issue or a big issue, or enforce primary key foreign key by splitting the car model, right? The car maker and car model separate in a separate table. This is what we call normalization, right? Which we'll see formally in the next set of slides, right? But the fact that what we do to fix this is that we split it. We say this data should have been captured elsewhere, right? And then we can now that that it's separate, we can force this to be a primary key, right? And now we can have uniqueness, right? Where this is captured only once, right? That we have Corolla is only captured only once, right? And then you have the car maker, right, combined with it, right? So we split it. We say that this is a foreign key. The car model Corolla references this car model over here. And by the way, this particular car model, which only occurs once, right? So here Corolla occurs only once, right? We capture the fact that it's a Toyota only once, right? Because we have this uniqueness. Now the dependency is still there. Right? The dependency is still there, but you have that it's a key-based dependency, not it's a what we call a full key dependency, right? Full functional key dependency. All right, that makes sense, right? So we have removed the risk of inconsistency by splitting it up into separate tables. Make sense? Here's another example. Where we might omit. Let's see, missing many to one. May produce right. So if you remove many to one dependencies, you might have this problem. So for instance, if you have professor teaches exactly one course, right? You have this section one to many to the professor, right? We might decide, right? At some point, we might have decided that there's no need to make the relationship between the professor and the course, right? Because we might have decided that perhaps we removed it because we thought it was redundant because we could go this way, right? There was no need to have a relationship between the course and the professor, so we might have removed it, right, to remove the redundancy, and we ended up with something like this, where we have the section ID is a primary key, the course ID is a primary key, and we have a foreign key that goes to the course ID, right? So the section has a foreign key to the course, it has a foreign key to the professor, right? And that might not be an issue. Requirement of exactly one course. We know the function of the. Oh, right. So these are foreign keys, right? Professor is a foreign key and course ID is a foreign key. But because we're revising and looking at our requirements, the requirement said that it teaches exactly one course. Well, that means that if you know the professor, you know the course, right? If you have this foreign key, you know also this foreign key. But there's no way for me to enforce this because foreign keys do not enforce uniqueness, right? Remember that, right? Primary keys enforce uniqueness, but foreign keys do not. Right? So I can have any combination of this over and over and over, right? Repeat it over and over. So you have a non-key based dependency between these two, between the professor and the course ID. So that means that there's no way for me to enforce that this professor only teaches one. All right, so the professor is not a key; it's only a foreign key. So what we could do is to instead capture the professor, capture the relationship between the professor and the course in the professor table, right? So where you have in the professor table, you have the professor ID that we still have the foreign key from the section to the professor, right? But notice that we have removed the relationship between the section and the course. Remember? Right, we used to have the relationship between the section and the course, right? The section and the course. We're going to remove that. Instead, we're going to move this relationship into the professor table. So we're going to remove this, and instead we're going to go this way. Okay? We're going to go this way. And what we do is that we move the course ID into the professor, right? Which is a foreign key, so there's one to many here. And we say, but the professor ID occurs only once, right? So I cannot. There's a uniqueness there. So now this depends on who, on the professor, right? On the professor is only introduced only once. So we have removed the redundancy again. Normalization, right? But we'll look at normalization formally in the next slide. Normalization tries to fix what we'll see certain types of functional dependencies, right? Very, very specific type of functional dependencies that occur over and over and over, right, in database design, right? And it tries to identify those and then split it into, in a certain way. Okay, so we'll see that in a second. But it's the same idea, right? We split it and we create a separate table. All right, let's look at normalization. Okay, yeah, so normal form. So again, what we're looking to do is to look relationships that we might find between fields, right? We're not talking about relationships across tables, right? We're considering a particular table, right? And all the fields in there, is there anything wrong with the fields amongst each other, okay? Attributes that we might have found when we were discovering these attributes. The first one, right, so as I introduced earlier, yes.
Is there a link to the slide deck?
It should be on Piazza. There should be a link. It's all the it's not there?
In the order. It's there, but not in there.
Wait, let me see. CS5200 resources. Or normal forms. There it is. Yep, it's there. Okay. Right, there's a link at the bottom that says show more. And you can see all of them. It only shows the first 10, I think. Right, but there's more in there. What was I saying? Right, so normalization. So as we saw in the previous presentation, the idea is that we identify problems between the fields, right? And the way to fix it typically is splitting those fields, that instead of being in the same table, they should have been in separate tables, right? So that's a general solution. That these attributes should have been classes in the first place. Right? So let's look at the first problem. These are classical normalization issues, right? Classical dependencies between fields, right? That might be wrong, that might have some issues. So here's one of them where we want to capture. Here's a customer table. We have the first name, the last name, and we have the phone number for that particular customer, right? But then somebody thinks, says, you know what? I might want to capture several telephones, right? Because not only do I want their mobile, I want their work, right? Maybe I want a fax number. So I want to capture all these telephone numbers. So how do I do that? And there are several naive ways to capture this, right? One solution might be that I decide to capture this in comma-separated lists. It says, well, I'll keep my field, my attribute telephone, right? I'm just gonna grab all my telephone numbers. I'm gonna concatenate them, right? Separate them by commas and put them in that table. That's one of the typical solutions, right? One of the problems in there is that now your data, right? The data you've just introduced there is no longer queryable, right? Because it used to be that you can query against a telephone number. Now it's not just one telephone number in there; it's actually a string made up of several telephone numbers, right? So you can't, now it's a problem with indexing. Whether I can use it as a query, give me the customer whose telephone number is, right? That query no longer works, right? It's no longer useful because now the telephone is really a set of telephones, right? But it certainly doesn't work for that one particular customer, right? But in general, that it becomes useless. The other naive solution would be that for every version, for every instance of that new value, right, you would decide that says, well, I'm not going to do that. Instead, I'm just going to have, I'm going to create as many columns to capture the various telephones, right? And you know, I'll create at least maybe 3 or 4 columns, expecting that you know, people or customers are not going to have more than 3 or 4 telephone numbers, right? Now this causes this for this table. One of the problems is that this table is going to be somewhat sparse, right? You know, where you're going to have lots of nulls everywhere, right? Because perhaps most customers are only going to give you 1 phone number, right? And you have this extra space that you've allocated, just in the chance that perhaps maybe you'll get a 2nd or 3rd or 4th telephone number, right? But most of it is just going to be empty, just nulls everywhere, right? And this is very, very typical in database design. You find it all over the place in industry, right? It's a very common issue that you either you have flattened your model, or you have over designed, right? For fields that you might use or you might need in the future that you don't really know, but you want to be you want to make sure that, you know, we might need this field at some time in the future, right? And it turns out that they never use that field, right? And you look at their data, and it's just nulls everywhere, just empty data. There's all these very sparse tables where that have you know 50 fields, of which they're using the first 4, right? You have 44 fields that are just not used anywhere, right? So you want to avoid that as well. So this one's not good either. So what another solution, right? It says, well, I'll keep the 1 telephone number, field. What I'll do instead is that for every different telephone, right, I'm just going to reintroduce a new record, right? So in this solution, notice that we are capturing the first name and last name more than once, right? So again, that introduces redundancy, right? Because if it's really the same person, right? And there's no way for me to enforce the fact that if I change one, the other one has to change as well, right? If the customer decides that they don't want to be called Billy, it should have been William from the beginning, right? I run the risk of updating record 456, but not record 457, right? And if tomorrow I ask, what's the first name for a customer whose last name is Squire, it will come back with 2 answers, right? One is Billy and the other is William. Well, which one is it? Okay, again, inconsistency, right? We want to remove that inconsistency. We don't want to have bad data. We want the database to stop us from introducing bad data. Okay? All right, so what to do? Right, so typically the solution, as we'll see all throughout these types of normalization exercises, is to split, right, a field, an attribute that should have never been an attribute, right? It should have been its own table, its own class from the beginning, right? So here the telephone numbers is the candidate, right? That instead of capturing each record twice or several in one field or separate columns, it should just be its own table, right? So here's telephones that, wait, what is this pointing? It's pointing to the wrong thing. What? Oh, it's doing it right here. Oh, there's no WYSIWYG, huh? Aw, man. Oh, I bet because it's wait, let me see. Probably because I'm scaling. No, it's still. Anyway, see if that works. All right, that looks a little better. Right, so instead of having 2 records, we have these actually the arrow should go the other way, right? These are 2 telephone numbers, right? Who has a foreign key of referencing back the original record. So these are the 2 phone numbers for that particular customer, right? 456 and 455. 456, right? These two records reference saying that they both belong to the same user, right? So we split it into two tables. Make sense? Right? And these are all the same. So we call this, again, this is so common, right? This problem is so common, right, that we give it a name, right? It's the first normal form, right? It has a first name and last name, right, and a middle initial. Right, so common we give it a name. Here's the second one. Here's the second normal form. These three that we're going to look at are so common, right, that you should become familiar with them and how to solve them, right? They're so familiar. Here's another one that says we have, and this one deals with primary keys that are compound primary keys, right? Keys that are a combination of two fields, well, two or more fields, right? So in this case, we have two fields, right, that combined make the primary key, right? So these two fields where we have the course ID and the semester, that has to be unique, the combination. The combination of these two fields has to be unique. So for instance, we have CS5200 in 2009-1, CS1500 again 2009-2. So semester 1, semester 2, semester 3, I'm guessing. Then notice course CS5200 taught in 2009, 2010, right? And not okay, so that's okay, right? Those are the combination of those two is unique. That's fine. But then we have the other two. We have places, right? Meaning how many students are allowed, perhaps, and then the course name. Okay, the course name is programming, databases, web design, right? So here we're noticing that there's a dependency between the fields, right? Notice that if I know the course, right? If I know that it's course CS1500 or CS5200, right? Well, there can only be one course name, right? CS1500 can only be programming, and CS5200 can only be databases. Okay, so there is a dependency. And what's wrong with this dependency? What is wrong with this dependency? Well, it is a functional dependency. Is it a key or non-key functional dependency? Well, it looks like it's a key functional dependency, isn't it? It depends on CID, which is a key, isn't it? Right? But actually, right, it depends only on half the key, right? It's not depending on the whole key. You see that? And that's our problem, right? That the field course name only depends on half the key, but not both, right? And that's why this was called the whole key, right? We say that to remember these three normalizations, we say the sentence or the paragraph, it has to depend on the key, the whole key, and nothing but the key. Okay, to be able to remember these three normalization, right? The first one has to depend on the key. Okay, this one has to depend on the whole key, not only half of it or 2/3 of it, on the entire key, right? And the third one, which we haven't looked at yet, we'll see that and nothing but the key, right? But let's keep looking at this one. Let's look at how to solve this. One way of solving this functional dependency is that the courses should have been a separate table, right? From a get-go, right? Instead of having the name of the course part of that bigger table, right? It should have been its own table, right? Where you capture the course ID once and you capture the course name once, right? And then these could be foreign keys, right? I'm sorry, those course ID over there could be foreign keys back to this table, so that you can always join them, right? And retrieve what the name of the course was, right? So instead of redundantly just repeating the name of the course, right? Just capture it once, right? Again, we split into a separate table and we join them with keys, right? Here's another example where we have Alice. So we have a list of employees on the left-hand side. and we have skill also. So the combination of employee and skill is a primary key, right? We call it a compound key, right? It's a combination of employee and skill that has to be unique, right? You can't tell me that Alice is a QA more than once, right? It makes no sense, right? But I can tell you that Alice has lots of skills, right? Alice has a QA, CSS, HTML. Bob has jQuery. Charlie has Java and C#. Dan has jQuery. Okay, right? And I might also want to capture where are they working. They're consultants, and on Mondays and Wednesdays they consult in Cambridge, and Tuesdays and Thursdays they're in Newton. Okay, I want to keep track of where they are, right? And so, for instance, one way to capture it is saying, okay, well, here's Alice. I know the skill, and I want to capture where they are, Cambridge. Okay. Notice that right away, there's a problem here that nothing would stop me from saying that Alice with QA skill is in Cambridge, and the next record entering that Alice with CSS skills is in Newton. Nothing is stopping me from introducing that bad data, right? It would be inconsistent. How could Alice be in two different places at the same time? It makes no sense. I want the database to stop me from doing things like that, right? How do I enlist the database from stopping me? Well, I could have, again, the solution is usually the same, right? The current location should be a separate table, right? Where the current location is only captured once for each user, right? And then you have Alice could be a foreign key to this other table, so I can always retrieve where is a particular employee, right? So yeah, so we have a dependency. We have the current location depending on who? It depends on the employee. Given the employee, I should know where they are, right? They can only be one place, right? They can't be in two different places, right? Knowing the employee, I know the current location, right? So there is a dependency, but it depends on half the key, right? It does not depend on the entire key. Make sense? So again, typically what we do, we split, and we have foreign keys that relate these two tables, and we capture the employee only once and the current location, and we can join these two tables to ask, what are their skills, who they are, and where they are, right? Make sense? Okay. But notice this example, it does not break first normal form. It does not break second normal form, but it still allows us redundancy. Okay, let's look at this. We have a combination of keys, course and year, right? Course and year, and let's see. We have the professor who taught web development in 2012 was Alice. They also taught in 2013. Alice also taught Intro to DB. Let's see, Bob Marley taught Intro to DB and Web Dev in 2012 and 2013. And Charlie Garcia taught C++ in 2011. And notice that we're also capturing their date of birth, right, for the professor, right? And notice that both the professor and right, they both depend on both of them, right? And but not only do they depend with the fields, but notice that they depend on each other. See that? Right? We have that the date of birth depends on who you are, right? You can only have one date of birth. It would make no sense for you to have two date of births, right? So this one you have dependencies between fields. So we have a non-key functional dependencies between the fields. So they're depending on each other. So not only do they depend on the key, but they also depend on each other, right? And that's what we say that this is a. We say that this is the last sentence in that paragraph that I said earlier, that you depend only on the key, the key, the whole key, and nothing but the key, meaning don't depend on any other field, right? You only have to depend on the key, meaning if I give you the key, I know exactly what data you're going to give me. right? It's like when you index, right? When you're doing an index, right? And took algorithms. Typically when you do a hash table, right? And you compute an index, and you only put one item in that index, yes? Right? If the index, the hash function, tells you that it's the same index, what do? You have to do collision, right? You have to handle that collision, right? You either go to the next one, or you do a linked list, or whatever. You have to handle that collision, yes? There can't be two different things in the same location. It makes no sense, right? Same thing here. If I know the key, right? If I know the key in a record, there can only be one piece of data there, right? And that data should be unique. It makes no sense that I have two different keys and I have the same data, right? That would be redundancy, right? I don't want to have that. So anyway, so to fix this, again, the way we're going to fix it is by splitting this into a separate table where we have the professor and the date of birth is captured only once, right? And then we have references back to the original one, right? To the original table. So in this case, it would be the professor being the foreign key that allows us to join these two tables, right? And we say that this is fixing third normal form, right? Where we have fields that depend on each other, except instead of just depending on the primary key. That makes sense? All right. So these were example cases. In the midterm, you're gonna have something similar, right? I'll give you a schema to start off with. I'll ask you identify the functional dependencies. Some functional dependencies will be okay, right? Because you'll have the right-hand side depending on primary keys. That's okay, right? And some of them will have non-key functional dependencies where you have fields depending on the fields. Right? So you're going to ask you to list all the functional dependencies. Tell us which ones are okay, which ones are not okay, right? And you say, well, these three are okay, these four are not okay, right? And I'll ask you why. Which one does it break? Does it break first normal form, second normal form, third normal form, right? And I'll ask you to fix it. And typically what happens, you'll have to split it right into two different tables and say, how do we join? Here's the new schema that fixes first, second, third normal form. Make sense? Right? Okay. Obviously, there'll be an assignment for this. All right. How are we doing with time? 7:17. All right. Let's take a quick break. All right, and then we'll come back right after these messages.